Good afternoon.
Hello there.
Okay. All right, folks, remember I'd like to see your smiling faces, or at least your faces. They don't have to be smiling. There is no smile requirement on Zoom. And we will go for where we need to be. All right, so today I wanted to start going over the acidity, basicity stuff, which will enable you to do the extra credit exercise. Not sure if anybody's done it yet. Has anybody had the pleasure yet? Dubious pleasure?
Yeah, I did it.
Did you complete it?
I did.
Oh, okay. Well, that's pretty keen.
It was lovely.
Was it
It was
fun?
lovely.
Yeah?
I particularly like the really hard stuff you put in between, so we had to do it 600 times.
Yeah. Yeah. Now tell me, at the end of it, do you think you understood it?
In a automatic sort of way, but not in a consciousness sort of way.
Oh, that's unfortunate.
I was able to do it, but I'm still not sure how.
Oh, okay. So it's kind of magical. All right.
It was a magic.
Okay. Well, let's see if maybe seeing it in class today might help you out a little bit more with it.
I was hoping.
All right. Okay, so let's look at, we're looking at acidity and basicity today. I think we are. Yes, we are. So let's first of all talk about acidity of aromatic hydrocarbons. We've already dealt a little bit with this when we were talking about aromaticity. But the example I'm looking at here, well, first of all, let's give a little bit of some background here to some Ka and pKa. Let's do that. So this is the typical acidity type situation. And we'll also do a tip. Sorry?
You're not sharing your screen yet, I'm sorry.
I'm not sharing my screen. You know, I'm not. That makes it so difficult.
It does.
Let's try this again. Thank you, Donna. I can imagine going halfway through the class and nobody saying anything. That would be pretty horrible. Okay. All right. So you think after doing this many Zoom things, I would have learned to do that. But anyway. So taking you back, way back into Chem 2, I'm sure that you would have covered this kind of stuff. And what you can see here is that Ka is essentially proportionate to the concentration of H+, which means that if Ka is higher, or as Ka is high, then H+ is high. And that means, that's another way of saying that, is acidity is high. Because that's what acidity is. It's the presence of H+. So the bottom line there is, if acidity is high, Ka is high. Is everybody okay with that? Does anybody have any questions? Anybody have any questions? Okay. So what that means is we can also then talk about another concept, and that's pKa, which is the negative log of the Ka. But because we're taking a negative log, what that means is that situation gets reversed. And what we can say is that acidic, higher acidity means lower pKa. So that's what the little p means. It means take the negative log of the Ka. So higher acidity equals lower pKa. That's what we have to aim for here. Does anybody have any questions? So when we're talking about these examples that I have on the slide, I've got this compound here with the 2 double bonds in it that has a pKa of 10. And then I've got the ring without any double bonds in it, it has a pKa of 50. Now the reason that the one that has the pKa of 10 is so much more acidic is because the anion is fairly stable because it's aromatic. You know, we talked about this when we were talking about aromaticity. But let's look back at the pKa values here. Now, when I say that one has a pKa of 10, the other one has a pKa of 50, that doesn't mean that the one that has 10 is 5 times more acidic. It means it's 10 to the power of 40 times more acidic because it's a log function here and we're talking about exponents. So 50 minus 10 is 40. So 10 to the 40th more acidic is what we get from that. Does anybody have any questions so far? Now, when you talk about a regular alcohol, like, for example, ethanol, that has a pKa of around 15. It's pretty close to water, which has a pKa of about 14, which is the pH scale, if you remember, the top of the pH scale. There's a reason for that. You'll notice, though, that this kind of alcohol, where the OH is actually attached to an aromatic ring, has a pKa of 10. So it's a lot more acidic than a regular garden variety alcohol because the anion is a whole lot more stable. So if you look at the anion for the alcohol, it's going to be the O minus plus the H plus. That's the anion there. This anion's a whole lot more stable because the negative charge can resonate around the ring. So this is about 10 to the 5th times more acidic than garden variety ethanol. Does anybody have any questions? So if you look at some of these other pKa values, like for sulfuric acid, it's minus 3.0. That's really low because that's really acidic. And even the sulfonic acid here with the aromatic ring in it is about negative 2.9. So, you know, we're getting really, really acidic kinds of conditions here when we talk about negative pKa's. We already know sulfuric acid is a strong acid. Does anybody have any questions so far? Now, if we talk about benzoic acid has a pKa of around 4.23. So there is some kind of stabilization granted to that anion, that benzoic acid anion, because if you look at just a plain ring that isn't a benzene ring attached to a carboxylic acid, you'll see the pKa is about 4.73. So it's not a huge difference in acidity, but the benzoic acid is a bit more acidic than just that regular one with the ring on it. And again, it must be because that aromatic ring is imparting some sort of stability to the anion. Anybody got any questions so far? So if we just look at some examples now of what happens if we take benzoic acid, which is the one here with the acid group on it, and then we've got phenol over here, which has the OH group on it. You can see what the pKa's are. The carboxylic acids are always going to be a whole lot more acidic than the alcohols because of the resonance with the double bonded oxygen here. But you can see if it's 4.23 for benzoic acid, 10.00 for phenol. Now, if we look at what happens when we add electron withdrawing groups, now electron withdrawing groups, and that's another way of saying deactivating groups. And what we're talking about there are these groupings. I'll just remind you of these because we talked about these earlier. And I'll just put the aromatic ring down here as well, just to highlight that connection there. So if we're talking about those, the other ones we got are EDG, which is electron donating groups, and that's activating. And those are the OR type groups and R2 type groups. I'm just trying to think what else are the alkyl groups. I think that pretty much that's pretty much all of those, I think. And so these are electron withdrawing, these electron donating. So you can see if we look at the electron withdrawing groups, look what happens to the pKa of each of these when we add these electron withdrawing groups, like this nitro group, for example. You can see what happens is that the pKa drops from 4.23 down to 3.49 for the benzoic acid and from 10 to 7.15 for the phenol. Then if we put in electron donating group, it has the opposite effect. It raises the pKa of each of these to 4.48 and 10.91 respectively. So what's happening is that if we take a look at the benzoic acid with the, actually we'll take a look at the phenol with the nitro group on it. And then we look at what happens when we take the H plus off. So that's a negative there. What you'll see is that we've got the electrons being sucked towards the nitro group here, which is actually a stabilizing type situation relative to it not being there. And we'll say plus H plus as well. But I won't draw the other one beside it, so you can compare them. So with the activating group, you can see that the activating group has a destabilizing effect because it's pushing electrons towards a negative charge. So I'm hoping you can see the effect there of those different groups, the activating group and the deactivating group, and how it stabilizes or destabilizes a negative charge.
Can I ask a question?
Yeah, Julie.
Okay, so this has to do with the quiz.
Yes.
One of the problems that I had in there that I didn't really come to terms with, which there were actually two problems, and they were, actually there were three problems. One of them was, if it increases the acidity, does it automatically decrease the basicity?
You have to consider them separately, Julie, is the answer to that.
Okay, that answers the question.
Because they're different animals. Because with acidity, you're looking at concentration of H plus. With basicity, you're looking more at concentration of OH minus.
Okay, so I get that part. So to start with, you have to know whether you're looking at an acid or a base to begin with.
Yes, okay. That's right.
That was the part that I had the biggest problem with. And then also, you worded it so that it said added electrons to the, it didn't say added electrons or take away electrons from the ring.
Right.
And all the way you're describing it, you're talking about adding electrons to the ring, taking electrons from the ring. But the way you worded it had to do with the lone pair. So does that make it different?
Not really.
So it's still adding and subtracting to the ring?
Yes.
Okay. And then the last question, I forgot, but I'll get to it again when you do the next ones.
Okay.
I have a quick question.
Yeah. Mm-hmm.
So with the nature of the activating and deactivating, whether it's making it less acidic or more acidic, is that really just specific to the benzoic acid and phenol derivatives, or is that in general for aromatic?
It's in general compounds? It'd be in general for anything, because anything that's got a positive charge on it will help stabilize something that's negative, Donna. And likewise, anything that's pushing electrons towards something negative has a destabilizing effect.
Okay, perfect. Thank you.
But we're only talking about the anions here, the negatively charged species, not the actual compounds themselves before they lose the H plus. We can't say much about those. All we can really talk about is the anions, right? So I don't think that's too bad. I think that most people can kind of get behind that. Does anybody have any questions? Because I'm happy to talk about this for as long as we need to here.
So activating group stabilize the negative charge.
No, an activating group will destabilize the negative charge because it's pushing electrons into the ring and therefore pushing electrons towards negative charge, Miriam.
Okay, so because they're pushing so because it's same charge, it makes it more
destabilizing.
Destabilize. Yeah. Okay. Yeah. So activating group destabilize the negative charge, and deactivating group stabilize the negative charge because they pulled. Okay, thank you.
Yeah, because you're pulling negative charge away from the anion. That's good, because it's going to go towards that positive charge. So, the opposite charges are kind of an attractive, lower energy type situation.
Okay. So does that mean it's opposite when it's bases?
We'll see, Julie. Okay. Let's not spoil the surprise.
Okay.
Yes, spoiler alert. Yes, I think that's true.
So, quick question.
Yes, Jasmine.
On the exam, because I was looking at it, I was a little confused with these reactions, but now it's starting to make a little bit more sense. So you just label if it's deactivating or activating, where if it's stabilizing the charge and the general reaction then for because I saw on the exam number, I think it was like the 2017, you're supposed to just label everything and where the ion, oh gosh, I can't talk, and how it reacts basically.
Mm-hmm, mm-hmm.
And
but I'll get to that. You got to give me a chance, Jasmine.
Okay, I know. I'm cool. I'm just thinking. Sorry, I'm thinking ahead. Mute myself.
Yeah, it's okay, but I'll get to it. Do you think I was just going to leave it be? No, I wasn't. Okay. Any other questions about the? Any other questions about the? I will show you how it applies to the test in a bit. Okay. All right, let's take a look at basicity. Now, basicity is a different kind of story. Let me. Okay, let's get rid of that. Okay. Now I've shortcutted this a little bit, but I will just show you something here. If you've got something that's negatively charged and you put it in water, it will become this kind of situation. And what makes it basic is the production of OH minus instead of H plus. I'll show you a second example here. That's if that was A minus, but if it was A, just A that was neutral, then that would form AH plus OH minus. And this is what we're dealing with. The source of H plus is usually going to be some sort of solvent, but that's what bases do, is they take H plus from something. And when they take H pluses from something, we get what's called a conjugate acid, which is going to likely be positively charged if we start off with something neutral, which is the example that I have over here. So in the case of the previous one, the anion can be looked upon as what we call a conjugate base. And here the cation is called a conjugate acid. Now looking at the basicity, just with something regular here, if you're looking at aniline, it has a pKb of 9.3, and if you've got just a regular nitrogen here with alkane groups attached to it, or alkyl groups, it's going to be 4.0. So there's a big difference in basicity here. The same rule applies to basicity as applied to acidity, and that is the lower the pKb, the more basic it is. The reason that aniline is so much less basic is because the electron pair on the nitrogen is interacting with the aromatic ring, and it makes it less available. And what that means is that it's less prone to take an H plus. So that's why we find that anilines end up being less basic than their regular alkyl amine counterparts. Does anybody have any questions so far?
I'm so sorry. I do have a question. Going back to just the generic, when you were leading into this, you gave the example of if you have something negative, you put it in water, it produces OH negative. Mm-hmm. Great. But then you gave a second example where you put a neutral and it produces the cation plus the anion, the OH minus. What was the point of that? I mean, what were you? I missed what you were trying to call out there. I'm sorry. Well,
actually, I wasn't really trying to call out anything except to say that bases produce OH minus when they're put in water, but it depends on the nature of what you're putting in the water first as to what you get as a conjugate acid, whether it's going to be something neutral or something that's got a positive charge on it.
Okay, so the conjugate acid is actually the AH,
yes,
not the. Okay, perfect. Thank you. All right.
Now back up over here, the conjugate base is whatever we're getting along with the H plus, so the anion. These are acids and they're becoming the conjugate base. These are bases, they become the conjugate acid. So looking over here, this is what I've got is the conjugate acid. So what happens when we add H plus to these, and these can go back in the other direction and release H plus and become these bases again, going in the opposite direction. So those you'll notice for the amine, the aniline, it's going to be a whole lot more acidic than the amine H+. So what you said earlier is true, Julie. What's true for acids is the opposite for bases.
Okay, but I didn't understand the last sentence you said before you said that. You said it becomes more acidic?
The conjugate acid of the aniline is more acidic than the conjugate acid of the amine. If you look at the values, 4.7.
But it's less basic.
But the original compound it came from is less basic, yes.
Less basic.
But we're talking about now the conjugate acids. You've got to compare apples to apples here, Julie. So for bases, we're talking about the pKb values. That's on this side of the arrow. And once they gain the H+, then they become conjugate acids. And we can talk about pKa's for those, but that's on the right side of the arrow.
So when you're asking it on the test, or let's just say on the quiz, I don't know if the quiz is the same as the test.
It pretty much is.
It gets a little confusing.
Yes,
When you're asking about, do you ask it different ways each time? Like sometimes it says conjugate acid and sometimes it says base. Like,
yes.
Is that it? Or
yeah, there's two different kinds of questions. Yeah.
So just because it says base at the end doesn't mean we're really talking about the base.
Right. If you're asking about the conjugate acid, then you've got to consider the conjugate acid. But if I'm asking about the base, then you've got to consider the base.
Okay. So when you're talking about stabilizing, for example, sometimes it stabilizes it and sometimes it destabilizes it depending on how you ask.
Yes, it depends on what you're stabilizing or destabilizing, because what stabilizes a base destabilizes a conjugate acid. Or what makes something more basic will make a conjugate acid less acidic, sorry. So what makes, I don't know, is that I don't know if that's something I can, if I really cleared anything up for you at all there, Julie.
No, you did. It's just confusing when you're doing it, but I mean, I get it. That was one of the problems that I had because I kept trying to decide, if it was an acid or a base, and then it was deactivating or activating. And I got that, like that concept was no problem, but then I couldn't decide if it was going to stabilize it or destabilize it.
Right. Well, what you'll find is, and this is now, Julie, this makes it real easy. Anything that's negative will be destabilized by something positive. Well, sorry, anything negative will be stabilized by something positive. Anything positive will be destabilized by something positive. Okay. So if we're talking about, again, these electron withdrawing groups and electron donating groups, you can see the effect that the electron withdrawing groups have on the basicity. So you can see that the basicity decreases. This is because the nitro group now is pulling the electrons even more off the nitrogen here, whereas the OMe group is adding electron density to the nitrogen, which increases the basicity. So you'll notice that the basicity is opposite to what happened with the acidity. What was stabilizing in the acid case is destabilizing in the basic case, because we're looking at two different things.
So if you just think of it as like a line where it's acidic on one side and basic on the other side, it's still going in the same direction. It's just when it's more acidic, it's less basic. But does the deactivating and activating groups work differently on it?
No, well, I mean, they have the opposite effect. I mean, in the case of, look what happens to the basicity here. Do you see how it goes from 9.3 to 13 with the electron withdrawing group? Becomes less basic, right?
So if you know that the deactivating group is going to make something more acidic, and you just know that,
Yeah.
that would hold for the bases too, because if it's more acidic, it's less basic.
Right, but what I would say is that the electron withdrawing group is having the opposite effect on the base that it had on the acid.
Okay, so the stabilizing part's going to be different, or the taking and giving electrons.
Yeah, do you see what happened here in this case, Julie? The electron withdrawing group actually had a stabilizing effect on the anion.
Right.
So it made it more acidic, made the compounds more acidic. Whereas over here, you can see it makes the compounds less basic.
So is that going to affect the giving? And this is only because I don't understand necessarily about the electron pair.
Well, the electron pair is on the amine here. It's on the NH2.
Right.
And if you've got an NO2 group, it means it's sucking that away, making it less available to the H plus that it's reacting with.
So my question is yeah.
So this is the situation. There, that's the lone pair on the NH2, and if you're reacting it with an H plus, then the less available that is, because it's being sucked away from something, then the less able it is to latch onto that H plus, which makes that less basic. Now, if you have a OMe group, that pushes electrons into the ring, which makes that electron pair more available, which makes that more basic. And you can see that's reflected in the numbers. Is that okay?
It's okay, but I still don't understand. Is the deactivating group always going to give electrons to the pair?
No, the deactivating group will take electrons away from the pair.
I mean, I'm sorry, that's what I meant. Well, is a deactivating group, whether it's an acid or a base,
yes,
it's still going to give and take
away
the same way?
Yes, absolutely.
So the only thing that's really changing is what it's stabilizing versus what it's destabilizing.
Yes, that's true.
And whether it's more basic or more acidic.
Right.
Okay, that helps. Thank you.
Now, when we consider the pKa of the conjugate acids are these guys down here with the pluses on them, the AH plus, as I had over here. And you'll see that it has the opposite effect to what we saw with the bases, but it's the same effect to what we saw up here with the acids, because these are acids that we're talking about. So we've got 4.7 as the pKa of the aniline conjugate acid. And you can see that when we put a nitro group on there, a deactivating group, that destabilizes the positive charge and makes it more acidic, because it's going to want to get rid of this positive charge by becoming H plus, because it doesn't want to interact with the nitro group, which is also positive. On the other hand, if we put in an activating group, the OMe, which is activating, that's going to stabilize the positive charge up here, which makes it less willing to give up the H plus, which makes it less acidic. So you can see the numbers here, 4.7 for the one that's not substituted, 1.0 for the one that is, and 5 for the one that's substituted with the deactivating group, and 5.2 with the activating group. So again, it's the same kind of effect, it's just opposite for the acids. Does anybody have any questions so far? Okay. So the last thing I've got here has to do with the basicity of aromatic compounds. And what we notice for aromatic compounds like this one, pKb is 14. You compare that to the pKb value we've got of anilines, for example, with the NH2. But when the N is part of the ring and the aromatic ring is actually including the lone pair of the nitrogen to give it 6 electrons, then that makes it very unavailable for interaction with anything. So you'll find that the pKb is very high, very much higher than you might expect it to be for a regular nitrogen. Whereas in the case of pyridine, it's pyrrole, in the case of pyridine, where the N lone pair is not part of the aromatic system, you'll see that the pKb is a whole lot greater. It's 8.8 as compared to this one, which is 14. And again, it's reflective of the fact that the lone pair is more available to interact with the H plus than it is in the case of pyrrole, which has the lone pair as part of the aromatic system to give it 6 electrons. So that's what I'm trying to say there. Does anybody have any questions about that one?
So the pyridine is more acidic?
The pyridine is more basic than the pyrrole. Yeah, because it has a greater attraction for the H plus. Julie? Okay, so things that give up H plus are acidic, things that take H plus are basic. All right. Let's take a look at some of the. We'll look at the test questions first, and we'll see. And now there's 3 possibilities for the test questions, essentially. I'm going to outline them for you here. So this is question 5 that we're looking at here. So for the first part, it's going to be acidity. Actually, I'll cancel the. I'll just get this part here because I still probably want to try and keep the other part for now. Okay, so this is number 5 that we're talking about. So the first part is acidity of a carboxylic acid or a phenol. That's for the first part. For the second part, it could be basicity of an aniline or acidity of a conjugate acid. So those are the 3 possibilities for these 2 questions, but the first one is always about acidity. So let's see how we might go about doing a question like this one on the top here. So I'm going to get rid of that because I want to keep the other thing present. So looking at the first one here, what you've got to do first is figure out what you're looking for. It says which one has the higher pKa. So high pKa means less acidic. So what you want to look at is what these look like as anions in order to figure out if the group that's attached is going to have a stabilizing or a destabilizing effect on the anion. So you'll notice what I'm doing here is I'm taking off the H and leaving the negative charge where the H was. So in the case of the first one, you'll see that we've got an activating group, which is going to push electrons into the ring. And we've got the NO2 group, which is going to pull electrons out of the ring. So you'll see that the activating one has a destabilizing effect, whereas the NO2 group has a stabilizing effect on the anion. So what I would do is I'd start at the bottom here. And I would say that this is going to be, well, we want pKa higher, so the answer has to be less acidic. And if it's less acidic, it's because it's destabilizing the anion. And what will destabilize the anion is the activating group, which makes it compound A. So you kind of work it backwards, you know, from the bottom up towards the top, and it just makes it a bit easier that way.
I have a question.
Yes.
If it's less acidic,
Yes.
it's more basic, it's still destabilizing the anion of the base?
Yeah. Well, the conjugate base, it's, well, let's, Julie, don't talk about basicity when we're talking about acidity. I think you're going to confuse yourself.
But the anion is the conjugate base.
It is, but then that makes it more basic, doesn't it?
Right, but it's not destabilizing the anion or destabilizing the conjugate base. It says it's destabilizing the anion of the conjugate base.
Right, which it is.
But is it? I thought you said the anion was the conjugate base.
It is.
Okay.
It makes it more, it does make it more basic by destabilizing the anion. It makes the anion less stable. Yes, that's true. I'm not denying that. But that's what has the effect of making it more basic. But we're not going down that road. All we're talking about is the compound and how, if it's acidic or not, or less acidic or more acidic. So the answer there would be less acidic because it destabilizes the anion and it's activating since it's compound A. So you can just circle those. That's how you can answer it. Does anybody have any questions?
Will you ever ask for the pKb in that question?
Not in that question, no. In the bottom question, I possibly could, Courtney.
Okay. So the first question's always identical. It just could be lower pKa instead? Yeah,
that's correct. But it could be either a phenol or a carboxylic acid, but you would handle them the same way, Courtney.
Okay, thank you.
Okay. Any other questions about number 5 here? Okay, let's look at number 6. So I told you number 6 could be about basicity, or it could be about the acidity of a conjugate acid. So for that one, I think the top one, most people seem to be able to get. I don't think people generally have, that much trouble with the top one. This one seems to annoy people. So it is asking about the conjugate acid, so you should probably draw what the conjugate acid looks like. Now the conjugate acid is going to look like this. It's going to have the H plus attached to the nitrogen group of the aniline part. Okay, so again, looking at whether we've got activating or deactivating. We can see what effect these are going to have. Now, the activating groups will always add electron density, whereas the deactivating groups will always subtract electron density. So that's where the adds and subtracts comes into play. So in this case, we're asking which one is, in this case, lower pK, which one's more acidic? So which one is going to be more inclined to give up an H+? So the one that's more inclined to give up the H plus in this case will be the one that's on the right-hand side, the one with the nitro group. So we need more acidic, and that's because it subtracts electron density from the N lone pair. And that's because it's a deactivating group, and that's going to be compound B. So if you look at that, you've got positive, and then you've got positive. So it wants to lose the H plus, so it can become neutral and it's no longer interacting with what amounts to a partial positive charge down here. That's what makes it more acidic. Does anybody have any questions about that? If you look at the other one, you can see that the methyl group there is, this is on the left one. The methyl group is adding electron density to a ring. It's stabilizing that positive charge, which makes it less acidic, makes it less willing to go up that H plus.
Wait, I'm sorry. I thought if the N has a plus there on the left-hand side, and
Yes.
we're adding electrons to it, I would think that would be more stable, not less stable.
Well, it's more stable to the conjugate acid, but it makes it want to give up the H plus. So it makes it less wanting to, less able to give up the H plus, because it is more stabilizing for that, for the N plus. But it is adding electron density into the ring, and therefore to the nitrogen lone pair. I don't think I've said anything that's contradictory. All right.
Well, I'm sorry, I feel foolish. In the previous example with the carboxylic acid, for instance.
Yes. Yeah.
You have an activated group.
Yes.
That destabilized it.
Yeah, that was a negative charge. Yeah, that was a negative charge though, right? Wasn't it? This is a positive charge.
Correct.
Yeah. So so it's going to have the opposite effect on a positive charge that it had on a negative charge.
Okay. Got it. Nope, you're good. Thank you.
All right. Okay, anybody got any other questions? All right, let's talk about how you can practice this. Now there's a quiz here to help you practice this. And that's the acidity basicity quiz. I also have this PDF document here, which is acidity basicity problems. Let's look at that first. So that can be helpful too, and there are answers to this as well. At least with regard to being able to figure out what's more acidic and less acidic, etc. Okay, so that's a resource for you to look at. Let's look at the quiz here though. Okay, so this is the acidity basicity practice quiz. You need 100% on this to open the credit quiz. Donna, what's the other catch to this? Since you've done it, well, you need 100% on it. So what's the catch to it though? And you can take it as many times as you like.
It doesn't show you what the correct answers are.
It doesn't show you what the correct answers are. That's right, Keisha. It doesn't. It is evil. It is evil. What's the other catch, Keisha? Do you know?
Besides it being hard, I don't really.
the other thing is that the questions are from a pool. It's not the same questions each time.
Okay. I don't know what it is about this particular concept, especially when it gets to basicity. I'm kind of with Julie. For logically, it all makes sense, and then when you ask the questions, my brain just mixes it, and I don't know I don't know why. So for whatever reason, this particular concept just vexes me so.
Okay. So for this one here, which compound has the lower pKb? So we're looking for the one that's more basic. I don't know, that NH3 plus really shouldn't be there. That should be NH2. That's kind of annoying. Anyway, it's the same kind of thing as if what you're being asked to do on the test, but you can still answer the question here regardless. Oh, no, it's fine. No, I'm lying. That's all right. Because it's the NH2 group that's going to be basic here. All right, so it's still all right. So this is a deactivating group, and this one here is an activating group. That's why it's positive. So you're being asked to kind of fill in the blank here, and I think there's 16 possibilities, and you've got to figure out which one it is. So lower pKb, so that would be the one that's most basic. That would be the one that has the activating group on it. That'll be B, because it's pushing electrons into the ring and making that more negative, which enables it to attract the positive charge more. So the answer will be compound B has an activating group which adds electron density to the ring and makes the compound more basic. So you'd figure out, you'd find the option that matched that particular logic.
Is it safe to say that, I think I might have asked this already, but I just want to ask it again. Is it safe to say that if a deactivating group is going to make the original thing more acidic or less basic?
Both of those things are true.
But it's going to move it towards the acidity, a deactivating group, no matter what it is.
All I can say is a deactivating group will make something less basic, and it will make the conjugate acid more acidic. I think that's reasonable to say. An activating group will have the opposite effect. Activating groups will tend to make things more basic and will tend to make conjugate acids less acidic.
And regular acids too, right?
Yeah, regular acids as well, if we're talking about the destabilizing or stabilizing of the anion. That's correct, Julie.
Okay.
But the effect of acids and bases is completely diametric. It's completely opposite. Consider which one has the higher pKa. So which one is less acidic? The one that's less acidic will be the one that has the activating group on it, because that's going to destabilize the negative charge. So for that one, it'd be compound A has an activating group which destabilizes the anion, making the compound less acidic. So again, you can sort of do it backwards: less acidic, destabilized anion, activating group. I think that's a good way of doing it. Anna, do you have a question?
Norepinephrine is mostly associated with.
Sorry, I didn't quite catch that. Did somebody? No? Okay. So, do you have any questions?
For the pKb, would it just be the opposite answers pretty much?
Pretty much. I mean, what I'm saying for acids is what stabilizes anions, destabilizes. Yeah, it makes things less basic. Is that okay, Courtney?
Kind of, yeah.
That didn't sound very convincing.
Yeah, I don't really know.
Let's see if I can find another one here. Okay, if that one didn't even have any, that one didn't even have any conjugate acid questions on it. I'll re-roll it and see if I can get it to come up. Maybe there aren't any, I don't know. I thought there were.
Did you save them for the credit quiz?
Well, yeah, I guess we'll have to find out, won't we? If you've already taken the credit quiz, keep your mouth shut, please. Here we go. This is an example. Which compound has the conjugate acid with the lower pKa? There we go. So for that one, you want to concentrate on what this looks like with the H plus attached to it. So to be NH3 plus. This is deactivating on compound A and it's activating on compound B. And we're looking for the lower pKa, so the one that's more acidic, and that would be the one that has the deactivating group. So Julie, what you said earlier is true. So even in the case of conjugate acids, the deactivating group is going to increase acidity. Do you hear me?
Yes.
Yeah.
Thank you.
I think that makes it easier too, if you can think of it in those terms.
Right, because then you really only have to worry about whether it's stabilizing.
Well,
And
we have to
You
worry.
already know it's whether it's donating or
Yeah.
taking away based
That's
on.
right. Yeah, that's
So
right.
you have to figure out whether it's stabilizing whatever it is you're asking.
That's right. Yeah.
And stabilizing means that it's not going to be acidic, right?
Well, in this case, it's not even really asking about stabilizing anything. It's asking about what it's doing to the electron density from the N lone pair.
Yeah, it's the stabilizing ones that I have the problem with.
Right. Well, the stabilizing ones aren't really these, but you can still make the same kinds of predictions as we made in the previous ones with this. So we get a universal effect on acids, we get a universal effect on bases, and they're opposite. Deactivating groups are going to make things more acidic, we'll say that, and activating groups tend to make things less acidic. Deactivating groups tend to make things less basic, and activating groups tend to make things more basic. I think that those are fair things to say.
I'm sorry, could you write that down on your board?
No. All right. Okay, Keisha.
Thanks. I didn't quite catch that. That was too quick.
All right.
Thank you.
Dr. Musgrave, do you feel like your mini lecture videos for this are pretty like correlative to the test and the quiz?
I think so.
I'm gonna have to watch those like a million times to get there.
All right, here we go. Deactivating groups increase acidity and decrease basicity. Activating groups I'll be decrease acidity and increase basicity. Is that okay?
But what about the stabilization? Do they stabilize, or do they stabilize the same thing, or I don't understand the stabilization.
Well, look, all I can tell you is that in the case of anions, deactivating groups will stabilize anions and increase the acidity that way, right? So I will actually add that in here. Increase acidity and stabilize anions. I don't like that. Hang on. Is that fair enough, Julie? Activating groups will destabilize anions. I think that's the only time you have to worry about stabilizing and destabilizing. Right? Is that okay, Julie?
Yeah, but you don't use it for the bases? You don't ask about stabilizing when you're talking about the bases?
Don't quote me, but I don't think so.
But can I ask just so I would know?
What I think from memory, and this is all from memory, and from what I've seen here, I only ask about the effect it has on the N-lone pair when we're talking about bases, which is not talking about stabilizing or destabilizing at all.
Okay.
At least in the questions.
Okay, but would it do the same thing, or you don't know? I mean, on the cations?
Well, are you talking about stabilization now?
Right.
Why are you asking me about something I'm not even going to ask you about, Julie?
Okay, I just am curious. That's all. It's okay.
All right, okay. You're asking me, I'll tell you. All right. A deactivating group will destabilize a cation and make it more acidic.
Okay. Thank you.
All right. Activating groups stabilize cations and make them less acidic.
That answers it. Thank you.
Okay. But I'm not asking you, I'm never going to ask you that. I won't do it. All right. Any other questions about this?
Dr. Musgrave.
Sylvia.
Question. So deactivating subtracts electrons while activating adds electrons, correct?
Yes. That's true, Sylvia.
Thank you.
All right. Any other questions?
I just want to make sure I got it right. So if it's activating, it decreases the acidity, it has a lower kPa, it destabilizes, and it attracts less electrons.
Okay, you have to repeat that, Jasmine. Okay, I'll take it one step at a time, okay? And I'll say yes to each portion, all right? But don't ask me to do the whole thing at once, okay?
That's fine. I'm sorry, I'm probably nervous. So if it's activating, it has a lower kPa.
pKa.
pK. Oh gosh. It lowers the acidity.
Start again. Start again. I want to make sure I do not want to get this wrong. So start again.
Okay, so if it's activating,
Deactivating, yes.
Start with is basically if it's acid or if it's not. That's just an easy way to start.
Okay.
And then if it's more acidic, it will basically increase the base. It's destabilizing and it has less electrons. I think that's what I wrote. Maybe I wrote something wrong.
No, activating groups will add electrons.
Add, okay, that's what I did wrong. Thank you.
Deactivating groups subtract electrons. And activating groups for acids will raise the pKa, not decrease it, Jasmine.
Thank you.
Okay. Other questions? Other questions? So the other good thing that this quiz does is it helps you with your knowledge of activating and deactivating groups. I mean, if you can't figure that out by the time you've done this quiz and gotten it correct, I don't know, you know, you got to figure out where you're at with that, because it should be, there's no way that you can get this quiz right and not understand activating and deactivating groups, because you get to see all sorts of examples and you get used to it. So I think it's worth doing. It's a hard quiz, I will admit. It is a hard quiz, but it's doable. A lot of people end up doing it, and it's worth extra credit. All right. Does anybody have any other questions about this? All right. So the test, I believe, it's next Thursday. Is that correct? Next week, Thursday next week.
Yeah.
Yes.
Yes. Okay. So Thursday of next week. So we've got 2 days here to review, and that's what we'll be doing. We'll be doing on Tuesday and just Thursday this week and Tuesday of next week. Nobody has any excuses. They can't say, oh, you know, I don't want to start studying until we've finished everything. Well, there goes that excuse. All right, we've done all the material. It's up to you now.
Professor, for this question that right now is on the screen, I see the B, well, both NH2 and OH are activating.
Yeah, but you're only interested, but look, it's if we're talking about a conjugate acid, then it's the NH2 group that's the basic group. That's the one that's going to have the H plus added to it. After that, then you're looking at the other group.
Okay.
So it's always the other group you're looking at. That's not the NH2, Miriam.
Okay.
Okay. Any other questions?
Can you post the last lecture, the one from Thursday?
I thought I did. You say I didn't?
No, I didn't see it.
Okay, I'll take a look, Billy, and I'll make sure it gets up there if it's not on there. Okay.
Okay.
All right. Does anybody else have any questions? All right. Well, we'll leave it there then for today.